Welcome to the world of decision trees.
So imagine a tree with branches and leaves. That's really the essence of a decision tree. It's a graphical representation of choices and along with their consequences, which guides us towards the best decisions. So decision trees make smart choices by splitting the data based on different attributes. So this division helps identify patterns and create branches that lead to accurate predictions. And so with each branch, the decision tree explores new possibilities. It asks questions, evaluates conditions, and so divides the data into even smaller, more manageable subsets. And then at the end of each branch lies a leaf. It's a powerful decision. It represents the outcome or the prediction based on the preceding choices, which give us valuable insights. Now, decision trees really excel at both classification and regression tasks. They can predict whether an email was spam or not, determine the price of a house, and even do medical diagnosis or prognosis. Also, one of the greatest strengths of decision trees is their interpretability and traceability. We can really trace our way back from starting from the leaf all the way to the root, which makes us understand the path that led to that final decision. So decision trees are based upon divide and conquer algorithm or top-down learning where you start by finding the root node and then you start recursively creating branches and then creating different subsets of your data that will go under each one of the branches that you've created. So for instance, you can create the first node in your tree, which will be one of the attributes, for instance, the Outlook attribute, and then you create different branches for different attribute values like sunny, overcast, rainy, and then you break down your initial data set into different subsets that will go down each one of these paths depending on which attribute value they correspond to. For instance, all the instances that have Outlook equals sunny will go down this path, and you do the same for the other attribute values, and then right after that you recursively create another tree node that will correspond to another attribute, for instance humidity, and then you recursively create branches and so on. So the algorithm stops at the leaf node once once all the instances have the same belong to the same class. So coming to the question of how to select an attribute, which attribute should we select as our root to start our tree with? So among the different options, the ID3 algorithm uses a metric that's called the information gain, which we will talk about next. And the goal is to choose the attribute that is the purest. And so when we talk about an attribute that yields a pure result, we speak about this example, for instance. So if we go down the overcast branch, Outlook equal overcast, we can see that all the instances that belong to this leaf actually are classified as class yes. They all belong to class yes. So this is a pure leaf. This one make our decision very easy. And so for the next time you have a new instance that goes down this path, you simply you do not need a lot of information to make a decision. You will automatically predict the class yes because it is the majority class here and because this is a pure leaf. But again, how can we measure this purity metric? So we use something called the information to measure that, and it is in a unit of bits. So the idea is we need to know the amount, so how much information it is expected, it is needed to classify a new instance, right? To specify whether that instance belongs to class yes
or no. So we want this amount to be as small as possible, right? We want to be able to easily classify instances into the class yes or no. So the information is usually less than 1. And we're going to learn today how to calculate this metric.
So as we said, the information or the entropy represents the amount of information needed to classify an instance. So the entropy is actually a 0 at a leaf where we have all the instances belonging to the same class. So for instance, all the instances belong to class yes, then this makes our job easy because we will automatically predict class yes for all the instances that will go down that leaf. So there were not much of an effort done, so there is no information needed to do this prediction. Therefore, the entropy or the information there is 0. However, if we had equal number of instances belonging to each class, for example, 2 yeses and 2 nos, then the information or the entropy reaches the maximum here because it's really a tie and it makes our job hard to predict one of the classes. So the ID3 algorithm uses the information gain metric to decide the root node as well as all the different nodes on which we're going to branch our tree. And so the information gain is simply the information before splitting minus the average information after splitting. So there is more details in Zybooks on how to do the different calculations, but remember that the ID3 algorithm will calculate the information gain for all the possible attributes and pick the attribute that has the highest information gain as the root.
Now to continue building our tree, we just continue splitting recursively in the same manner. So once we decided that Outlook has the highest information gain, we fix the root and we do the same operation down the tree. So we're trying to determine what node is going to be next. Is it temperature, humidity, or windy? So to decide that, we said we're going to calculate their information gains, and we notice that the humidity has the highest gain. Therefore, we fix humidity to be here in the next level, and again we continue similarly.
And so ID3 is a basic algorithm for constructing decision trees. However, we do need more advanced methods to construct a tree, and that method needs to deal with numeric attributes and handle missing values and handle noise in the data, and that's what the C4.5 algorithm offers us. So for the first problem, which is dealing with numeric attributes, the way the C4.5 algorithm does is using discretization. So you break down your continuous variable or attribute into 2 or more intervals. And so since there are different options to where the breakpoint of the interval should be, what this algorithm does is evaluating each one of the choices. So it will calculate the information gain or another metric for each one of the possible breakpoints and then pick the one that has the highest metric, for instance, the highest information gain. It is very computationally demanding, however, it's very successful, and that's what makes decision trees very accurate. And so coming to the second problem, which is missing values. If you have instances that have missing attribute values, like this test example right here. So here we speak about testing. So how does the C4.5 algorithm deal with testing instances that have missing attribute values? So the way this algorithm deals with this problem is you go ahead and follow the path down your decision trees that you have constructed during training. right? And so you know that the outlook for this instance is sunny, so you go down this path, and then the next attribute is humidity, but you don't know which value. So you check your training data, and for instance, you have the binary split here. If humidity is smaller or equal to 75, let's say from your training data, you know that there's 2 instances here that belong to class play, yes, and then probably there's 3 instances that belong to class don't play. So then what you do is you assign your testing instance to the majority class. In this case is don't play. So it's like giving the outcome in a form of a probability. So there is a 0.4 probability, which is 2 over 5, that this new day belongs to class play, yes, and there's a 3 over 5, which is 0.6 probability that this new day belongs to class don't play. And so the algorithm will choose the class that has the highest probability to predict. Now, if the problem of missing value happens during training, not testing, then the C4.5 algorithm calculates a modified information gain metric where it does take into consideration the fact that you have some training instances with missing values. So the modified information gain will actually be the same gain that we showed the way how to calculate before, multiplied with some sort of a weight that takes into consideration those instances with missing values. So the SA here is simply the number of instances with that attribute, with different attribute values, and MA is the number of instances that have that attribute, that have a missing value for that particular attribute. And then for the G here is you calculated exactly the same as we showed before, except that when calculating the entropy or the information, you do not take into consideration those instances that have missing values. So you do not include them in the frequency count. So one of the powerful things that the C4.5 algorithm enables us to do is decision tree pruning. So what is pruning? It's a strategy or a solution that the algorithm does to prevent overfitting. And again, a reminder, overfitting is a problem for any machine learning algorithm where the model fits the training data very well, that it prevents it from generalizing to new testing instances. So pruning is one way to prevent overfitting from happening in decision trees. So basically you're trying to achieve something that looks like this tree right here. So you do not want an over complex tree that will overfit the data, and on the other hand, you do not want a very simplified tree that will underfit the data. So you want to find your way somewhere in the middle. So you want a tree that will get a good training performance as well as a good validation and testing accuracy as well. So pruning basically enables us to remove some of the branches in our tree to prevent the creation or the construction of an overly complex tree that will overfit the data. So now there is 2 ways to do pruning. There is post-pruning and pre-pruning. The pre-pruning strategy is not very common. It's basically the pruning operation happens as the tree is still getting constructed, while post-pruning is done once you have a fully grown decision tree. And so pre-pruning is not common because it may cause the algorithm to stop early, even before creating a very interesting relationship between the attributes, which may happen all the way at the near the leaf level if you were using post-pruning. So that's why most of the algorithms use the post-pruning strategies. The most common form of post-pruning is the subtree replacement strategy, where you get to replace the entire subtree. For instance, in this example right here, we get to replace this entire subtree with just a leaf. So coming to the question of whether or not, or when to decide whether or not to prune the decision tree. So what C4.5 algorithm does is to try to estimate the error if pruned versus if not. So if the error after pruning remains the same or decreases, then the algorithm decides to prune that subtree, because if the error remains the same, then that subtree did not really bring us any much more added value. So it's just an overly complex tree for no additional benefits. So we decide to prune it. Now, if the error increases, and that's what we do not want, then we decide not to prune that subtree. So there are statistical methods that C4.5 uses to estimate the error and calculate it, but we're not going to go into much details about that. Now, just remember that when talking about estimating the error, we may not want to estimate the error on the training data itself, because that will be we're not going to get a realistic estimate of the error, because remember, training accuracy is optimistic because the model has been trained on that data and it knows it and it fits it very well. And so you may want to use a external or a never seen subset or a validation data, or you can also call it a pruning data, on which you want to estimate the error of your decision tree. Now, regression trees, on the other hand, work for numerical data and numeric attributes. It is also divide and conquer algorithm. The way to construct regression trees is almost very similar to constructing decision trees, except with small changes, namely the criterion or the metric to choose the root and all the different nodes will be different. So for decision trees, for instance, we discussed the information gain metric, versus for regression trees, they will have different metrics. For instance, we will pick the root or the attribute that will give us the highest reduction in standard deviation, for example. And then when it comes to the other difference is the stopping criterion. You want to stop building your tree when the standard deviation of that numeric outcome becomes really small. So there's not much of a variation there in that leaf anymore. And then there will be different metrics or numerical measures to decide for pruning. So for instance, for decision trees, we said that we will estimate the classification error to decide whether or not to prune. And same thing applies to regression tree. We can prune regression trees, but they will have different measures on which we base our decision. And then when it comes to the leaf now, for the decision trees, we had the class, the instances class at the leaf level. Now for regression trees, what we have there instead is the average or the mean of that numeric outcome for all of the instances that went down that path. So they're very easy to understand, and they're also, just like decision trees, they're fast and they're very accurate.